Okay, you should be able to see my screen right now.
Hey, Fawaz, can you hear me all right? Hey, I'm definitely not muted now. Okay, good morning, everybody, or good afternoon or good evening, depending on where in the world you are. My name is Lucas Beeler. I am a principal architect in the CTO's office here at Hazelcast. And this morning, I am going to be talking about, drum roll please here when I share my screen. A blueprint for operationalizing machine learning with the Hazelcast platform. So I'm going to begin by talking a little bit about a common problem that we as enterprise software developers run into when we start dealing with data scientists and people who develop ML models. And that's the question of like, okay, someone gives us a model, but how do we operationalize that? And I'll also talk a little bit about the way that Hazelcast can actually help operationalize a model. And I'm hoping that this will be the first of several videos in a series that I'll be able to do over the next few months, where I will actually build out the system that I'm going to describe today for operationalizing a model. So I'd like to give a lot of thanks to Sophia Chang, who was a summer intern here at Hazelcast, who is a data science student at the University of California at Berkeley. I'm based at Hazelcast's headquarters in Silicon Valley, and I'm coming to you live from my apartment in San Francisco right now, where it's 8:05 a.m. But we have had interns from Stanford, Berkeley, and other great universities in the Bay Area over the last several years here at Hazelcast. And this year we had an intern, Sophia, who is a data science student at Berkeley. So her background is in data science, not in CS. I mean, her education has been focused on statistical learning, statistical methods, inference, things like that, and less so on sort of traditional computer sciencey notions like big O notation and computational complexity theory. So with all of that said, let me talk about what Sophia built and how it's been given to me as an enterprise software developer. So I'm going to play the role of an enterprise software developer who's been given a machine learning model by a data scientist, in this case, Sophia. And I know what it does, but I don't really know how to operationalize it. So with that said, let me go back to sharing my screen, and I'm just going to pull up my my IDE here. So I hope that everybody can see see my IDE. Here we have IntelliJ up, and one of the things that I wanted to initially share was, well, what does this machine learning model that Sophia built actually do? It's very rough code that came from a summer intern. We're going to polish it off over the course of this series and operationalize it. But the basic idea is that it is a movie recommendation system. So the actual ML portion, if you see here, is written entirely in Python and uses tools like pandas and scikit-learn, right? And as I said, it's a movie recommendation engine. So you give it a movie that you're interested in that you're known to like, right? Let's say I'm a fan of gangster films, so I picked Goodfellas, and I can run the recommender. And here I get back a list of up to a dozen other movies that I also might like, right? So I mean, Donnie Brasco, definitely a good choice there. Carlito's Way, another gangster flick. Pulp Fiction, gritty, violent, definitely makes sense. What you see on the left-hand column here are the movie IDs in the data set, which are backlinked to their IMDb IDs. And then in the right-hand column, this is a confidence score and how confident we are that if you liked Goodfellas, you'll also like this movie. Of course, if I were looking at something like, say, Toy Story, more in the kids genre, I could run this recommender again. I'd see a very different set of results. No gangster flicks here, mostly Aladdin, Balto, both Disney animated films. So yeah, overall the system works pretty well, and it's something that you might actually see if we worked at, let's say, our own equivalent of Netflix, BOSS or BOSS, big old streaming service. Big old streaming service wants to recommend movies to you that you're going to like based on movies that you've already declared to like or have given, 2 thumbs up to in the rating system in our application. So yeah, we have a recommendation engine that works. Let's talk a little bit about some of the challenges here. First of all, this is Python code. I am not a Python developer. I'm a Java developer, like most enterprise software developers are, right? Python has an extremely strong following in the data science community, as well as in web development with tools like Flask and Django, but it is not as strong of a language in in enterprise kind of back-end development. So if I want to build an actual application that's going to be deployed in my company's data center, it's probably going to be a Java app. So the question becomes, how can I operationalize this as a Java application, but keep this nice machine learning model that I have? And I'll talk about how Hazelcast can help us with that problem. The next thing that I wanted to mention about Python is that Python has one inherent problem as a language when it comes to modern multi-core architectures or symmetric multiprocessing architectures in general. Python as a language has this notion of a single interpreter lock, which basically means that it is a single-threaded language. If you want parallelism in Python, you basically just run more instances of the Python interpreter and allow them to communicate via interprocess communication. So executing Python well in a way that can take advantage of modern multi-core architectures can be a bit of a challenge. So let's talk about how Hazelcast can help us solve some of these challenges. So first of all, a brief overview of the Hazelcast platform. The Hazelcast platform comprises two APIs. The first is a stream and batch processing engine, and the second is an operational data store. You could see it as something like Apache Spark or Flink, the stream processing engine part of it, bolted on to a high-speed in-memory store, something like Redis, but significantly more powerful in terms of its queryability than simple key-value stores like Redis offer. So think of it as an in-memory data grid or in-memory database that is wed to a stream processing engine. And the really powerful use of this for a machine learning application is that you can structure your data transformation process, right? So data will come in from various sources, and we have an entire sort of universe of connectors around data sources, right? If you want to change data capture from databases, if you want to watch files on disk, if you want to get subscribe to Kafka topics, you'll have business events come in. You will transform that data. It might mean something as simple as changing text to all lowercase, which we have to do in this case, pun intended, because that's how the lookup of movie titles happens to work in the ML model that Sophia built for us. You might combine data. That's data enrichment. So taking something like a UUID and converting it into a full record about the object or thing that UUID identifies. And this combination stage can be done through querying the underlying in-memory data store. And then finally, we have all of the typical functions that one would expect from a stream processing engine. Those would be filtering, mapping, flat mapping, et cetera. And then you'll see here we have ML inference, and then this notion of drawing data to a sink or publishing it to a sink. And that could be a file. You could be doing, insertion into a database, et cetera. But yeah, this is the basic notion of the Hazelcast platform. And I'd like to talk a little bit about the way the ML inference runner works. So the cool thing about the ML inference runner in Hazelcast is that it actually supports fully managed Python execution. So while Hazelcast itself is a Java product that runs on the JVM, it has the ability to spawn from its single Hazelcast JVM process as many CPython VMs as you have cores on your machine. I have a 10-core machine in front of me, so it would spawn 10 CPython VMs and execute any Python code that you might have in a massively parallel way. It does this in an extremely elegant way. It actually takes your Python code, looks at its dependencies, prepares an entire Python virtual environment, packages that up, and then instantiates these processes that run continuously. So provided your Hazelcast stream processing pipeline is running, your CPython VMs will also be running, and it's very easy to communicate with those CPython VMs simply by using operating system provided interprocess communication. On Linux, this is probably going to be Unix domain sockets. On the Mac, given its microkernel heritage with Mach and new kernel, it's probably going to be Mach RPC. Mach interprocess communication. But the point is that every operating system provides an interprocess communication mechanism. We simply run gRPC on top of the operating system's IPC mechanism in order to communicate between the Hazelcast JVM and the subservient CPython VMs. So with that in mind, I'll actually go back and show you in my IDE a Java pipeline that has been built up in order to run this Python code. The code itself is extremely straightforward and comprises really only about 15 lines. Basically, in order to be able to distribute these Python packages, I need to set resource upload enabled to true in my Hazelcast configuration. Then I create a new Hazelcast instance. I then create the actual pipeline, and I'm just reading from a file source, which has the title of a film in it. In this case, it's Toy Story. Let's actually change this to Raiders of the Lost Ark, another one of my favorites. And it will write the output to recommendations.txt. So if we look at the pipeline runner, here you go, you see Java code set up to run the pipeline, and then you'll see this apply function where we actually invoke map using Python batch. And this actually is what creates the bridge between the JVM and the various CPython VMs. And we're going to write to a sync that's just a file. So we're going to be reading from a file and writing to a file. This is world's simplest possible Java wrapper pipeline that you can imagine. But if I go ahead and I run this, one of the cool things that you will notice is that, sorry, that was I want to run the full pipeline. Here we go. We're getting a lot more output. Hazelcast itself is starting up. It no longer runs in milliseconds as it did before. Believe me, the Python code will still run within milliseconds. It will actually run probably faster than it did when I just clicked run here in my IDE, running under the Hazelcast inference runner. However, we have to deal with the startup time related to constructing the pipeline. But keep in mind, this is a one-shot cost, right? In an actual production environment, the pipeline would be running continuously, just waiting for data to arrive, right? So basically waiting for someone to be, on their iPad, trying to figure out what movie to watch, and, a new movie title arrives, and we want to find out, what are other movies that if the users gave this movie 5 stars that they might also like. So you'll notice that we have, we have quite a bit of interesting output here. We'll see us actually creating a Python virtual environment. All of this is done, internally and in an entirely automated way by the Hazelcast Jet Python runner. Hazelcast Jet is one of the proprietary names for our stream processing API. So if you see that phrase used, it's Hazelcast Jet's referring to the stream processing API in the product as opposed to the operational data store API. But yeah, we basically create an entire Python environment. We install the necessary packages. We're installing protobuf, gRPC-IO. We're realized that we've got 10 processors and 32 gigs of physical memory. If you're familiar with the way that Python builds packages, we build wheels for the Python dependencies, and then we install the collected packages. And so we're installing pandas, scikit-learn, scipy, all the stuff that data scientists use. I mean, these are the core data science libraries in the Python ecosystem. And ultimately, our pipeline will run, and we get back in recommendations.txt, a new set of recommendations that we haven't seen before yet, which is what is related to Raiders of the Lost Ark. And what we see is predictably other action films, and even another film in the Indiana Jones franchise. So Indiana Jones and the Last Crusade is our second most preferred movie. Jurassic Park is number one. Waterworld. Notice that all of these, what they have in common is sort of an action adventure slash sci-fi sort of feel to them, right? So, or I guess you could say supernatural sort of feel in the case of the Indiana Jones films, right? So, yeah, this is actually another good set of recommendations. So what we've been able to do is we've been able to take Python execution, wrap it inside of a Java process, and completely manage the execution of that Python code in a massively parallel way, right? You know, we did it using world's simplest possible pipeline, which simply read from a file, wrote those recommendation results that it got from all of the machine learning and data science code running in the Python VM, which just took that and wrote it back to a file. You know, that's great for this simple demo that I'm showing you in my IDE. In fact, it's ideal for that, but it's probably not what we'd want to do in production. And what I was talking about is, you know, if we're enterprise Java developers and we're thinking about how do we operationalize and sort of productionalize within the context of an enterprise backend machine learning model, such as this movie recommendation engine that I have, you know, how can Hazelcast help us with that? And, you know, one of the next things that you probably want to think about doing is, okay, I've got this model, I want to provide a way to access it. The most common way that you are probably going to do that in the modern API first world of backend enterprise development, where everything is an API, is to make your model an API endpoint. We can imagine a very simple kind of application flow that works this way. There's a user on a tablet device that's browsing their movies for our streaming service, BOSS. And, you know, the actual UI here on the tablet device is populated by simply HTTP requests to a web presentation server. That web presentation server, when it needs to make a decision about what film titles to show, would like to make a call to an API endpoint that encapsulates our movie recommendation engine. So it will make a call saying Toy Story. It will get back, you know, a list of similar movies if this is a known, you know, 5-star film for this particular user. So one of the great things about Hazelcast is that it plays very well with the kind of standard Java way of building enterprise applications in the API first world. It plays very well with Spring Boot. And it even comes with its own set of connectors that can make prototyping API endpoints very rapidly extremely simple. So let me give you a really basic example of that. So one of the things that I sort of discussed earlier was that one of the strengths of the Hazelcast platform was the fact that it has this ecosystem of sources and of sinks, where you can take data from Kafka, you can take data from files on disk. We actually used the file ingestion source in our simple demo where we just got the title of a movie from a flat file. It can take data from change data capture of database events, and it can publish to sinks that are symmetric with those sources, right? Like files on disk, cloud object stores like S3, you know, it can insert them into databases, et cetera. Well, you know, REST, if we're talking about using a RESTful API, is usually going to run over HTTP. So one of the obvious questions that I might have is if I go to the Hazelcast connector hub, which I can find at hazelcast.com/hub, and I just do a search for HTTP. can I find an HTTP connector that will allow me to very simply have a source and a sink for listening to HTTP requests? And it turns out that indeed I can. And here is the GitHub project for it. One of the things that we really pride ourselves on at Hazelcast is that, while we are a commercial software company based here in Silicon Valley, the core of our product is fully open source and licensed under the Apache 2.0 license. And we turn a lot of our contributions back over to the community through relatively permissive open source licenses, almost always Apache 2.0. And we've got an HTTP listener that we can set up. It's part of the hazelcast.jet.contrib, the sort of community group of Maven artifacts that we can actually use to put a really, really simple way to get HTTP requests, for say a REST endpoint onto our machine learning code. So keep in mind, we've taken this Python ML model, we've wrapped it in Java, and now by simply plugging in this connector that we found here on the Hazelcast connector hub, which has a lot of other connectors as well, including those for change data capture from PostgreSQL, listening to Apache Pulsar topics, etc. We've been able to find this HTTP connector, which would allow us to put a very rudimentary way to take an HTTP GET or POST request and get the payload and use that to prime our stream, right? In reality, we'd probably like to do something a little more sophisticated, and that would be to use our various integrations with the Spring ecosystem to build a Spring Boot application, which tends to be the pretty standard way of building microservices-based applications in Java, right? And you might wonder, well, what's Hazelcast support for Spring Boot like? One of the other great things about being an open source company and being very transparent is we have a lot of documentation available on the web. So Googling usually works. So I'm just going to Google, and I'll just say, well, Hazelcast, Spring Boot, how can I use them together? And you'll see there's a great tutorial here on docs.hazelcast.com about getting started with Hazelcast using Spring Boot. And actually, over the next few sessions of this, I'll be doing Twitch talks, not really sure how often, but over the next few months, I'll actually build out a true, Spring Boot microservices endpoint that will run the movie recommender code. And more than that, I'll even demonstrate elastic scalability. We can imagine a scenario in which, it's not the middle of the day on Tuesday, it's Saturday evening. There's going to be a lot more people, using their tablet devices to stream movies. They're going to want recommendations. And we'll talk about how we can simply scale up the number of Spring Boot instances that we have and, say, place them behind a load balancer such that we can handle the increased traffic, right? And we'll talk about the ability to deploy Hazelcast-based applications on auto-scaling container orchestration platforms like Kubernetes or OpenShift. So yeah, that's where we're going. And I hope that what I've shown you here is that Hazelcast makes an exceptional toolkit if you are an enterprise Java developer and someone comes to you and says, we just hired some data scientists, we need to operationalize machine learning in our organization, and they're going to be giving you a bunch of Python code, and you need to figure out how to make that happen in the context of our enterprise backend. And we can manage Python execution in a massively parallel way. We can make it easy to wrap the ML inside of a standard backend microservices endpoint within your organization. And I'll actually be building that out over the next few sessions, as I said. So thanks, guys. Take care. And I guess I will sign off now. And my colleague Fawaz may be taking questions. I'm not entirely sure, but I'll need to switch to the Twitch questions interface for that. So yeah, I'm going to go ahead and end this now and switch to the Twitch interface.